I'd like to welcome all of you to this session of Control System Society meeting. It is my pleasure and a privilege to introduce our speaker here, Dr. Ratnesh Kumar. He is coming to us from Iowa. He's a professor there. Many accomplishments. I can go on and on and on for a long time here. He's a professor there teaching electrical engineering, mostly control system classes. He has many publications, many awards and stuff. So he's a fellow of IEEE, and you know how hard it is to become a fellow, and he is. That means he has major contributions in the area of modeling and simulation of the control systems. He has also served on a member of he has served on a member of editorial board of IEEE and ACM, and has been general program chair and also given keynote talks at IEEE and ACM conferences. Without further ado, Dr. Kumar. And let me give you this thing here. You don't want that one. Yes.
Okay, thank you, Haik, first of all, for inviting me. I guess all societies within IEEE have a distinguished lecture program. So when I became got selected for Control System Society, I thought, we should host our own versions of these kinds of talks. So we just created a technical chapter on Control System Society in Iowa. And that became a role model. Now other groups within the department are forming their own societies, like Computer Society, Electronic Society, and so on. So it's a great pleasure to be here, in the national capital. And then I'm using this opportunity to also visit my friends at Maryland. One of them was my thesis advisor when I was doing my PhD at Texas. Since then he has moved to University of Maryland College Park. And then I also took the opportunity to visit NSF and DARPA, because that's what we do. We have to we supervise, we teach undergraduate students, we supervise graduate students. And graduate students are actually paid to get their masters and PhDs. So, and for that we have to do the fundraising, right? So it's for graduate school, if you're planning to go to graduate school. Undergraduate school, of course, you have to pay your own tuition. For the graduate school, if you want to do it, that we pay for you to come and get your degrees. So I started in control theory, and then started thinking about, there are lots of high advanced control theories, but then eventually that control is implemented as a piece of software, right? There is notion of linear, nonlinear, optimal, robust. There are lots of theories for designing advanced controller. But eventually, it's an algorithm that's implemented in a software. And when you write the code for that software, no matter what theories you use, you still have to make sure that code. So your controller design may be correct, but the code you wrote for it may have errors. So you have to still test it against the properties that you had in mind. So, this is a talk that I prepared, and if it is going to be too technical, it may have some technical flavor. Feel free to ask questions. So the idea is, so I'm going to talk about Simulink Stateflow. That's one of the software tools that very popular industry-wide. Right, so if you are designing control synthesis, or even if you're doing signal processing, you're doing communication, the software that is available MATLAB is the maker of it, and the product is Simulink Stateflow. So Simulink Stateflow is a graphical interface to the software itself. And so so these are various domains, whether you're riding a car or flying a plane or running a nuclear power plant or a robot or a rail, even. So control is everywhere. So I was just talking to Haik and said, you think of control algorithm as your brain. So the brain makes the decisions. Eyes, ears, those are the sensors. We have 5 different sensors. And then we have limbs and voice. Those are the actuators. So in our day-to-day life, we decide what to do based on the sensor information that comes and making decisions about ourselves, how to live in this complex world. And that's what a controller does. It drives a car. Now, the technology is getting ready where the cars are going to drive themselves. Right? So there is not going to be, so self-driving car is already happening. If you live in Pittsburgh, you can ride one of these cars for free. Uber, right? You can call Uber taxi. And if you volunteer to be a passenger who wants to get a free ride on a driverless car, they will take you from point A to point B for free, just to test that system. So that's part of the testing. That's part of the validation. So you can test in the lab, but you have to also test in the real world. So the self-driving car is going to happen pretty soon, and it has all the sensors to detect the surroundings and make decisions to drive the car just like a human driver. So self-driving car, all the control algorithms would most likely be written in this Simulink Stateflow framework. And it turns out that software has such a huge penetration that that's the main source of error in all sorts of accidents. So, and there are several examples that you would have heard about in stories at NASA or Intel or in different places. So Intel had a error in their arithmetic computation, right? That was undetected in one of their chips had a computation. It was doing the computation wrong. And so although that was a hardware error, but eventually you start with a software description of your hardware and then generate that netlist and then make a chip out of it. There was an airplane, or there was a NASA or some spacecraft which had an error where they forgot to do this, the units that we use here to the metric unit. So here we use miles to measure length, but the metric unit uses kilometers. We use Fahrenheit here, but the metric unit uses centigrade. They're not the same. So somebody forgot to do that simple conversion, and one part of the system was computing in metric unit, other part was in the American unit, and then that led to just losing one of the aircrafts in the space, which suddenly disappeared. So it's important to catch the errors in the software, early in the design process. But it's a process of evolution. There is going to be bugs in most things, but then over time it gets corrected and perfected. So let me give how this testing that we have conceptualized, model-based testing, works. And so I'm going to start with a much simpler example. So here it's an example of a control. So there's a microcontroller where there's a control software that's controlling the motor, and so the motor can receive a signal which controls the voltage that applied to the motor. and that controls the speed of the motor. So as the voltage is increased, the motor will rotate and will achieve a certain speed. So let's say, and the user sends a command, sends a velocity profile, and also sends a start-stop command. So using that, the controller then controls this duty cycle, and that controls the voltage level, and that controls the speed. And then there is a sensor which measures, and that's an encoder which can measure the angle, and then there is an A to D converter that feeds that signal to the control software. So this thing can measure the position from which it can infer the velocity, and that velocity of the motor has to match what the user has specified. So, and then there could also be a fault monitor. That's another piece of software. So there's a control software, there's a monitoring software, which actually measures the inputs that are provided by the user. It also measures what the variables of the control software, a few other variables, and from there, if there is some error that is detected, it can say a fault has happened. So basically, even a software is an input-output system, a reactive software. So whether it's a hardware or software or a control system, you have inputs coming in, outputs going out, and then when you want to say whether a software is doing its job or not, you're going to have some requirements on the input and output pair. So if the input is X, output should be Y. There is some constraints on the input-output pair or sequence of input-output pairs. So for example, these are some requirements. I would say, first one says, if whenever a user presses the stop button, the motor is halted in next 4 time steps. So let's say it's a discrete time system, and the input is sampled every millisecond, and then command is issued also every millisecond. So 4 time step would be 4 milliseconds. So no matter what control system it is, it's going to have a discrete time. So the control is not continuously applied, or it's not continuously changing. So every millisecond, so when you're driving a car and you have a automatic braking system, ABS, so it's going to sense any kind of slip that's happening in the car, and that it's going to sense every millisecond or every so often and make some adjustments in the acceleration and the braking. Right? So in a car, the actuators are acceleration, braking, and steering, and then so those are the controller commands. So in this, so everything happens at discrete points in time. So when step is pressed, the motor should halt in next 4 steps, and then there's another. There could be, this is just an example. There could be other specifications. So. So if you haven't seen Simulink Stateflow, this is how it looks. So you can, so in MATLAB is basically a tool. There's a company called MathWorks in Boston who started developing tools for doing numerical computations, whether doing matrix algebra solving. So you can do a lot of numerical computations, integration, differentiation, addition, multiplication. Everything can be done using that. So, but then they added a graphical interface within that. So you can model systems, and it's hierarchical. So this is the top view. And if you zoom in, so there is something more inside. So this, for example, is how this is how the model of the motor looks like in MATLAB. You have some So any dynamics, if it is a linear system, so in a linear system, in order to model it in MATLAB, you need to do 3 operations. One is multiplication, another is summation, and the third is integration, or time shift. So if the time is discrete as opposed to continuous, because you're sampling, so all you need to compute the next value and next value. So this block gives you not the next but the previous value. 1 over z block is a delay block. It gives you the previous value. So if the input is coming here, this output would be the previous value of this input. Right, so you need 3 kinds of elementary computation, one is to compute the previous value, one is to add, and another is to multiply. And through that, you can basically represent any dynamics. Isn't that interesting? But you have to, put them in a network, right? It's not just random addition, multiplication, and delaying. So when we teach a class, we tell how to take an input-output system and represent it in this form, right? So that's so if this, for example, describes the behavior of the motor, and then there are other components that I'm going to talk about. If you zoom in here, these are different kinds of models. These are state diagrams, and the previous one was multiplication, summation, and delay, which is in continuous time. That would be like integration. So in a state diagram, what happens is the values are not continuous. So there is some variable which takes finite number of values, and so this is, for example, the model of the control software. So any software has a set of lines of codes. And so it starts from executing the first line of code, then the next line of code, then the third line of code, and there may be a go-to statement, so it goes to another line of code. So whichever line of code is executing is captured here. So this may correspond to the fact that currently certain line of code so this is the next line of code, and next. So when you have trying to model a software, you need these kinds of models. It's called automata model. So in automata model, you have nodes and transitions. It looks like a graph, nodes with transitions. So the nodes are basically program counters, right? So in a program, you have lots of lines of codes, and whatever line is currently executing, that's the program counter. And then one can also build program counters for or programs for not just control software but also monitoring the behaviors. So the monitors. Monitors are also software. So software has the state machine representation or automaton representation. So that's the difference between a software and car, right? And a car is a system or an airplane which evolves continuously in time. So the position and the speed changes continuously in time, whereas software it only goes from one step to next step to next step, one program counter to next program counter. So there's an internal clock in the processor which goes from one, so it scans one line and the next clock, next line, and so on. So the two have different behavior. So nowadays, if you may have heard something called cyber physical system, which is nothing but in the controls community, we have been always designing cyber-physical systems. Cyber is the software, physical is the plant. Together is cyber-physical system. So that's a new buzzword these days. But in controls community, if you're designing a controller for a ship, the ship is the physical part which has continuous dynamics, and the controller is always a piece of software, and that is an algorithm. It's going to be represented like these graphs. So the question we're asking, so the MATLAB gives you the feature that if you develop your controllers using Simulink or Stateflow. Simulink is for continuous dynamics, Stateflow is for, so Simulink is for physical components and Stateflow is for cyber components or software. But MATLAB gives you a nice feature that if you write your software in Simulink or Stateflow, it can automatically compile into a C code, and then automatically compile into an object code that a microprocessor can run. So all that can be automated. You don't have to write the C code yourself. You can, so instead of writing X plus Y, you actually draw a block which is the summing junction, which has input X and input Y, and the output is X plus Y. So you do this in a very graphical, nice way, and I'll give you some examples of that. So given that we can build our control algorithms, and that's doing complex computations involving all kinds of summation, multiplication, delays, and feedbacks and all that. And it can be automatically converted into code. So this is not going to run on the microcontroller. The compiled one will be running on the microcontroller. So and in order to test that, we have to apply some test vectors. So this may be correct, but the code may still have some errors. And the code has to actually run on a piece of hardware, and the hardware may introduce some of its own nuances, and that may also affect the computation. So the code, so there is the design of the algorithms in Simulink Stateflow in a very nice graphical manner, and that's translated into code. But the code is the one who's going to run on a physical system, so that needs to be tested. Question is, can I use this graphical representation of the code to compute the test vectors? Right? And that's the question, how to use the model to generate test cases. And also, we want to make sure these tests are testing all cases that the control algorithm can execute. So every case has to be covered. There could be multiple, the control algorithm can compute, depending on what input it receives, it may trigger one computation, another input may trigger another computation, right? So all that has to be tested. So that's the goal that we had. And so these are the steps. So you would start from a diagram like this and end up with test cases like this. So in this case, each test case basically has an input-output pair, a sequence of those. So it says, for example, this test case says that if you apply input 1, you should expect an output 0. If you apply input 1, the second input 1 should produce an output 1. Right? So that's one of the test case. So if you have seen that, then you've tested one type of computation. So in this case, there are 4. This simple example has only 4 test cases. So in order to get the test cases for testing the code that corresponds to this, we'll first translate that into the automata model that I talked about, which is basically a graph. right? A graph is nodes and transitions. That's a graph. But in this case, that captures that. And from that graph, we'll learn what are possible computations, which is, so this graph is basically starts from that top node, goes around and returns back to the top node. So there are loops. So each loop, starting from the top node, going through all the other nodes, coming back, is one control computation. So at any given time instant, the controller would monitor all its sensors, and then based on that, and based on the current state of the system, it will issue a command to all its actuators. So that's what is happening in each loop. It reads the inputs coming from the sensors and sends the outputs to all the actuators. And that keeps on happening at every time step. So at any given time step, one of those loops will be executed. And in this case, it turns out that there are 18 possible loops in this example. So one of those 18 choices will be executed at any given time. But that keeps on going, right? So every millisecond, this loop executes. And next millisecond, again, same loop, different loop in that may execute. So I'll go through these steps. Feel free to ask questions. So far, so good?
One question here.
Yeah.
Testing has been known to belong to a class of problems known as NP.
Yeah.
Which like similar to traveling salesman. And so how do you ensure that you really have all the test cases?
Yeah.
In theory, it's just like infinitum, basically, you know?
Yeah, that's, so yeah, I mean, so it's a hard problem, right? So but the thing is, there has been a lot of advancement, first of all, even for hard problems. So NP-complete problem like traveling salesman you talked about. The simplest, an equivalent version of that is called satisfiability. And so that's another NP-complete problem. And there has been tremendous progress. There are SAT solvers, satisfiability solvers that you can get that's in public domain that can solve with thousands of variables. So yeah, in general, it's a hard problem. But now there are tools that are available that that can solve the practical problems that we're dealing with. And this started, the issue of solving these types of hard problems started back in World War II, right? So we had to do lots of logistics. And so the problem of logistics was addressed at that time, which resource to send where and when, optimizing all that. It's basically operations research and boils down to satisfiability. So there's a long history of research study from 1940s. Danzig was one of the first people who came up with an algorithm called simplex algorithm, right? So it may not give you the optimal solution, but it computes fast and gives you something very close to optimal. And if you persist, you can find optimal if you have more time to do the search. So there has been tremendous progress. So lots of new heuristics, and also having so many powerful computers, the processing speed have gone up, right? So you can do a lot more number crunching now, right? So I mean, when you're imagine doing a Google search, that's probably an NP-complete problem, right? To find a bunch of keywords and get a listing of, it goes through all the billions of and then finds you an immediate result. How does that do that? So yeah, these are hard problems, but people have come up with very reasonable heuristics, which give you good enough answers. It may not give you the best answer, So if you want a journal paper written on a certain topic, Google will do that search. And then it may even rank them, order the one which is most cited first, and then the next one which is less cited. So that's what we use as some kind of methods to do that. Some of these problems are not just NP complete, they're undecidable. So there are some problems which you cannot solve by computers. They are called undecidable. So NP complete is traveling salesman. So those who don't know traveling salesman, right? Imagine a salesman who has to go to n different cities, right? And you may be a salesman one day, right? With your box that you have made. So Haik has made a box that he's going to sell, which is a nice model-based prototyping system, basically. So if you want to sell it, so you have to go from city A to city B, so you have to visit n cities, let's say. And you have all these interconnections between cities and distances, so you can plan a tour visiting all cities exactly once and do that. Well, you know, if at every city you have two choices, you can go left or right, then even if you have n cities, you have almost 2 to the power n choices. So the moment you have a number of choices which is an exponential in number of variables, it's an exponential problem, which is, you know, essentially boils down to, in many cases, NP complete. So finding an optimal path which visits every city and minimizes the distance, the total distance that one has traveled, is called the traveling salesman problem. And one can prove that there's no easy solution to it. So whereas, you know, if you, for example, doing Fourier transform or doing matrix inverse, you can show that if you have a matrix of size n by n, you can invert it in n to the power 3 at most, right? So that computation is only a polynomial in n as opposed to exponential in n. So that's the difference between the complexity. An exponential starts to grow pretty quick, so as n becomes larger, it just blows up. Polynomial will grow slower, it's more manageable. So if something is n square, n cubed, that's reasonable. People want actually n, linear, or even log n, logarithmic. Nobody wants exponential. But unfortunately, there are problems which are exponential. But then we have made tremendous progress by having good heuristics, by having faster computers, and also, you know, parallelizing. So maybe you can, you can divide and conquer. So you do a little bit. One processor does one part of the computation, another process, and they work together. So some problems can be parallelized. So a lot of weather modeling, you know, that's a complex problem. So when you're predicting where the thunderstorm is heading tomorrow, you have to model all that, and that's a complex computation in itself as well. So yeah, the complexity is there, and some problems are undecidable. So for example, if you have a polynomial, everybody knows a polynomial, right? Right. So like x to the power 5 minus 4x squared plus 2x. Let's say I have a polynomial. And everybody knows what a root of a polynomial is, right? Root means a value of the variable which makes the polynomial become 0. Right, so we want to solve the equation 4x to the power 5 minus 3x squared plus 2 equal to 0. We want to find an x which solves that polynomial. Now, if x is a real number, then if this polynomial has degree 5, because the highest power is 5, then there are going to be 5 different roots, at most 5 different roots. Now, but they are real numbers. Some of them could be fractions, some of them could be decimals. We want to know, does this polynomial has only integer solutions? Does it even have a single integer solution? So you don't want any decimal answer. You want a root, which is, so if x squared, for example, x squared minus 1 equal to 0, well then x can be 1, right? So x squared minus 1, so 1 squared minus 1 is 0. So x can be 1 for x squared minus 1 equal to 0. That is an integer solution. But if somebody gives you an arbitrary polynomial and asks you, does this have an integer solution, integer root, well, that's an undecidable problem. You cannot throw it at a computer and expect to get an answer. It's known that there is no algorithm that can solve that problem. Did you have a question?
No.
Oh, okay, right. So there has been understanding of complexity classes of problems, polynomial versus exponential versus not even solvable, and some of these problems are not solvable. But then in practice, even though it's not, so what happens is when you encounter a problem which is known to be NP-complete or undecidable, then you have to deal with them in a case-by-case basis, right? So in general, yeah, it's NP-complete. In general, it's undecidable. But in this particular case, it may have a solution. So you try, and if you're lucky, you get the solution, and a lot of practical problems that one encounters has that feature, right? So so that's why. So most of these algorithms are going to be kind of exploring, and there's no guarantee that it'll terminate, because it's exploring undecidable problems, so it keeps on exploring forever. But then, in many cases, it will terminate and give you an answer. And you can try, you can say, okay, I'm going to explore for 2 hours, or for 5 hours, or 100 hours. If you find an answer, if you don't, then at least you tried. So that's the idea.
For certification purposes, one is forced to only test the requirements and nothing outside the requirement.
That's right.
And that's, of course, called requirement-based testing.
Yeah, so that's a
but that doesn't test everything. In other words, you can go past the requirement-based testing, and now come back and the system will collapse.
Yeah,
under certain conditions.
Yeah, it does. It only tests for those. That only tests for. That gives you requirement coverage. Yeah.
No false negatives or anything. So.
That gives you requirement coverage. So, so if you have a code and you have a set of requirements for the code, if you just test the requirement, if the requirements is not complete, you will miss some cases. So there is requirement-based testing, and then there is just testing of the code. So this is more about testing of the code. And so if you want a FAA certification, so if you work for Boeing, for example, and you want to certify your control according to now new certification, you have to have certain kind of coverage of the test. Otherwise, FAA will not. FAA is the authority which approves everything in the avionics domain, right? That's a federal authority. Any other questions? So let me.
So the thing is, you were talking about model-based testing and then requirement-based testing. So where is the hierarchy in here? If I say, okay, I'm doing model-based, or am I doing requirement-based? In other words,
one should be doing both.
One is doing both.
Yeah, there's no one-fit-all solution. You have to throw all your weapons at the problem. Yeah, we shouldn't be taking any shortcuts. Yeah, so because no one is perfect. One set of approach may discover one thing, another set of approach may discover another thing. So let me give you some feel for what we do, and I won't take too much time. So for example, let's look at the Simulink. Appreciate it. Let's look at the Simulink diagram. So So there is a subsystem here, and if you zoom in, it has these components. And what's happening here is this unit is feeding in a constant 1 input, and that comes in here, and the output comes back and gets added. So this output is essentially going to be adding the sequence of ones. So this is basically a counter. Right? So if you keep adding 1 and 1 and 1, you'll get 1, then 2 plus 3 plus 4. So this is a sequence of 1 coming in and the sequence of 1, 2, 3 coming out. That's what is happening inside. And that output goes to the saturation block. So saturation block, it will saturate. So it will saturate in this case with the upper limit of 7. So as the counter keeps on counting, starting from 0, it goes to 7. Then after that, the saturation will saturate, and it'll keep giving 7 as the output. So the Simulink, has this library of these blocks. So you can pick a library. From the library, you can pick summing block, you can pick delay block, you can pick these kinds of inputs and just connect them, and that's how you build your algorithm. It's just, it's taking from library some cookbook computations that are already there, and then networking them, and that's how you get your entire algorithm. So what we have developed is a tool that will take this as the input and translate that into something like this, which is a graph, which does the same thing as that. But this cannot be analyzed mathematically. This can be analyzed mathematically. It's an automaton. So this automaton essentially is computing, starting from this initial node, going all the way across, coming back, doing one computation at one given sample instance. So it'll start with k equal to 0. That's the initial time, discrete time. At that time, some variable, this has a single memory. So you have to initialize that memory to some initial value. That is the initial count. So initial count is, let's say, 0, but you could also start at initial count as 10 and start counting up from there. So initially your count is 0 and your timer and the time is 0. And then it'll look at the input. If the input is positive, then it'll compute the next value, which is still 0. And if so basically depending on, so the input is coming at the top there. Input can be, in this case, a 0 or a 1. And when input 1 comes, this block is enabled, it'll count to next value. If the input is 0, this block is disabled, and in fact it will be, the count is reset to 0. That's this example is doing. So you have a sequence of 0 as 1 coming in, and depending on whether it's 1 or 0, the counter will count up or get reset. So if the 1 is there, then the counter will count up by 1. If it is 0, then whatever it has counted up to, it will become 0 again. But because of the saturation, then the output will never go beyond 7. All possible computations that can happen is shown here. So this is U represents an input, Y represents an output. So every time one of these edges is executed, the input and output computation is happening of that round. So the basic idea is that for each one of these atomic computation that Simulink can do, we have an edge here. In fact, 2 edges there. So the blue block has this edge and that edge, and this brown block has this edge and that edge. So in MATLAB, when this computation happens, there is a certain sequence in which these blocks will be executed. So for example, the blue block is executed first, then the red block. So this block executes, then that block, then that block. That's the sequence. Right, so although it's drawn like that, internally, for it to work, this will have to produce one value. This will set this output to the previous value, and then so now I have an input coming in, and I have an output coming in. Then I can do the addition. So this will compute later than these two. Yeah.
Do you have to have a subsystem which is linear, or you can do this for nonlinear?
Nonlinear, everything.
You still convert it to
yeah. So that you can still convert it to stateflow. So the nonlinearity will be labeled like these, so these computations could be a square. So this graph is really modeling the logic, if then else rules. So if input is bigger than 0, you compute this way. If input is equal to 0, you compute the other way. So it really capturing the logic of the computation. The computation itself is happening on the edges. So if it is nonlinear or sine, cosine, it still be happening there. Yeah.
What about an alternative view where you take all the values and calculate a new set of values without worrying about the order of the calculations? Say, well, instantaneously I have these inputs, and if I get all the functions and look at these outputs, and I just put those outputs into them.
Yeah, one can do that, but so the idea is to convert something like this into that so that we can analyze this, and we want to do this conversion in a sort of in a modular way. So these computations are already there. So MATLAB allows you, so there are some atomic functions that are in MATLAB, and you can combine them to get more complex computations. So we want to follow the same scheme. We want to convert the atomic computations into graphs, and then combine them to get the bigger computation. Right? So it's like in logic, you have AND gates, OR gates, NAND gates, XOR gates, and you can group them together. So there is atomic computations, and so this is a recursive modeling, if you like, and that's because just by looking at this diagram, there's no way to figure out what this whole diagram is doing. You have to do it recursively, because this translation is not done by human, it's done by machine.
Well, somebody decided on the order. And they're doing it to avoid the race condition.
Yes. Yeah, you're right.
Your circuit, yeah.
Yeah.
We used to have to do that in design.
Yes.
Okay.
No, so we are not claiming anything about race conditions. So there is an order in which MATLAB blocks compute. We borrow that order in how we sequence them. So our sequencing is same as the MATLAB sequencing, and we want to preserve, because we want this to have same computation as that. We will be use this to generate the test cases.
You're modeling the MATLAB model.
Yeah, and we're modeling the MATLAB model. And there is the reason is because we want to use the MATLAB model to test the code. So we are not there yet. This is one of the first step. Right? This is what is being used to create the code, which is running.
How do you prove that during the conversion your process did not make a mistake?
Yeah, so yeah, there is some, there is formal.
Outlier tool.
Yeah, there is formal.
That to that.
Yeah, there is.
Tool is good.
Yeah, there is.
Any mistake in conversion.
Yeah, there is a formal proof to this. Yeah, we have our paper. Yeah, there's one paper dedicated. We have a patent on this. So one patent just dedicated to this translation. And we have a journal paper which proves that there's a theorem in it which says that if you do this, then this and that are equivalent in terms of computation. Nobody else has done that yet. Yeah, go ahead.
Are those MATLAB statements?
These are, so that's the beauty of our translation, that you can simulate this in MATLAB, you can simulate this in MATLAB too.
That's what that's why I was confused, is because I was expecting you to say Simulink gives you these things, but inside these things are, a bunch of MATLAB statements. But they're not MATLAB statements. What are they? What are those? What is that language you're using?
These you're asking about, what are these?
Yeah.
So for example, so this, for example, corresponds to here, and all it's saying is set the output y3 equal to 1. So y3 is the signal, and that's what the meaning of this block is, that every time instant it sets y3 equal to 1. We're coding that explicitly. So whatever it's doing graphically, we're doing it textually.
It's your pseudocode.
It's kind of it's a flow graph with pseudograph code, because this one is easy to visualize, and you'll see in a minute why. We haven't gotten there yet.
It's a different representation.
It's a different representation. Yeah. So you can also do that, and I'm going to skip this part. For something like this, there is a Stateflow which has its own semantics, and we can convert the Stateflow into a similar diagram like before, and all this is done automatically. So our tool will take the Stateflow, which is that, and produce this automatically. So I haven't told you why this is useful, but this does the same thing as that does. So you can call it a pseudocode, but it's a different representation. And this is that tool. I'm going to skip that.
Can in the process it generate a state that is a trap state, and you go over there and you get out of it?
No, if the MATLAB has that issue, this will also have that. Yeah. So and you want that trap state to be there so that later when you analyze it, you can locate it, right? So this is, for example, the translated code, the translated version of the motor example that I started with. So motor example had all these Simulink Stateflow diagrams, and we can translate it, and not only translate it, this object is also recognized by MATLAB, and it can simulate it in MATLAB. And so this shows the example that I was talking about, the translated code and how the simulation of that. So you can simulate the original model, you can simulate the translated model, and visually verify that they are preserving the computations. So next, what good is that, right? I have to talk about that. So basically, so going back to the same example, there are two branches here, or actually three, 1, 2, 3. There are 3 branches here, and there are 2 branches here. So starting from here, going all the way back, you have 3 times 2 choices, so total 18 choices. And each choice is a certain sequence of edges. So for example, what is shown in yellow is path number 17. We have 18 different paths. This is the 17th one. So I have labeled each one of them. And each edge is representing a certain computation here. So this edge, for example, corresponds to receiving an input of 0, which will disable this subsystem and output a default output of 2. This edge is executed by the saturation, and it sees that the input to the saturator is 2, which is below the saturation limit, so it produces the output of 2. This edge is actually, so whenever the incoming input is 0, which is the case here, this subsystem block is disabled and the counter is reset, so this is doing that reset.
One question over here. Let's say you have a large subsystem, and you go through the conversion, and you get your diagram.
Yeah,
And they are really doing the same thing.
exactly.
No doubt about it.
Okay.
What can you say about the timing? Does it take the same amount of time to do this versus that in the processor? Or
Yeah.
does it take longer time to do this one?
Yeah, so the timing is such that, if my
Actual real-time on top.
yeah, real time. So if I'm running my control algorithm every millisecond, then this entire loop has to be computed within a millisecond, and that's a lot of time for a processor, because the processor now can do billions of computation in 1 second, right? So many megaflops, so many teraflops. So number of computation, so it will not even take a millisecond, it'll take a microsecond or even less to do this.
But I started saying large system.
Large system would still,
You see what I'm saying?
Yeah.
Getting bigger and bigger and bigger.
Yeah.
Putting pressure on the processor.
large system will still,
Still be there.
yeah. I mean, nowadays, because the processor speed has gone up so much, yeah, so
I can always find a large system.
yeah, if you can find a large system,
One bottleneck, right?
yeah. So, but we are not addressing that problem. That's a practical problem. So that's called the schedulability problem, right? So when you have a processor running multiple tasks, one of them may be the control computation. The other may be, you're running a network service. So you're running lots of tasks, and they have to be scheduled, and each one of them is going to take the time. And all that time have to add up to make sure it fits your sampling duration. That's the window of opportunity. And we live in the world with that window of opportunity. Whenever we said we're going to have this meeting at 6:30, well, we have some flexibility, and so that's we have that. So in real life, there's always, and so for processors also, although that millisecond, that actually looks like a very long time for a processor, because it can compute billion times or million times in 1 millisecond. So it's like living millions of lives. So that's a long time for a processor. It's computing so fast.
Does this language that you have help you better solve the problem of you set up the thing?
Yeah, I'm coming to that. So I'm just from this to that translation, what has done for me is told me that there are 18 ways this system can compute, and I need to test all of them. By looking at this, I have no way to figure out how many computations are happening, how many possible ways. So when an input comes, depending on what the input is, it can execute a loop, which is one computation, and it has 18 choices. In a large software, it may have 1 billion choices at any given time. So how to enlist them? This translation will tell you automatically, because now I have a very clear graphical representation, all the choices at so these are intermediate computations that are being shown in performing one sample. At any sample instant, the controller is making many intermediate computations to end up with a final result. This is showing all the intermediate computations and the sequence of those. And also possible ways of doing it. In this case, there are 18 ways of doing it. But imagine a complex software has millions of ways of doing it. And you need to test each one of them to make sure none of them has error, right? That's the idea. So that's what this has done for me, is it's told me these are the So it gives me a complete listing of all the possible ways a control algorithm will compute. So any other question? Yeah, go ahead.
At what point does this overwhelm your ability to actually list the...
No, this is just a running example. We are not going to list in a, so this is just to illustrate, right?
But if you're going to test everything, every possible, every evident loop,
so so if
does this sort of break down?
it doesn't break down because, if this control code is actually running on a microprocessor. So if it can run on a microprocessor, certainly I can do the translation on a PC. Right, so it doesn't break down. In fact, the translation is linear complexity.
But do you have to choose each one of them manually, say, okay, I tested this, or
Yeah.
process does that?
I have another tool does that. Yeah.
So that's answer to you. There is another tool that takes care of this. You don't have to worry about each one of these items.
It's linear complexity, so...
Yeah, so the translation is linear complexity. Finding the test case is not. That's NP complete. So that's... but as I said, just because it's NP complexity in hardness in worst case doesn't mean this problem that you are analyzing is the worst case problem. So now, for example, for this path to compute, every edge has a certain precondition. It says the input has to be below 0 then output will be assigned 2. Here the output, a certain output has to be below some value. So there's always a precondition for that to be satisfied. So if you have a sequence of computations with certain preconditions, together they may not be satisfied. So we can automatically, for any path, we can look at all the edges that are there and write them as a precondition implies the postcondition. And so the next is this precondition implies that postcondition. So whenever this condition holds, that computation will be executed. And make a conjunction of all those and ask whether this can ever be satisfied, right? So you can't have x greater than 5 as well as x less than 5, right? You can't have such a constraint. So so that's where NP completeness will come. You can throw this into a satisfiability solver and it'll come back and say, yeah, it's satisfiable. Meaning there is a certain input which will set the output in a certain way so that this condition is satisfied, so that happens, and then that happens. So this path, this computation is actually possible. But there is another computation where I just replaced this edge with that. That was path 17, this is path 16. It turns out that has a sequence of requirements that's not satisfied. So although there are 18 computations, it turns out that only 5 can really execute. You can't really, because these edges have some requirement, some guard conditions, and together they cannot be satisfied.